So, welcome everyone back to the class. The scope for our lessons today are we'll do some tips on the homework that we gave last time. It was, and I want your feedback because that sort of homework, I hope you realized the solutions are not easily available. You can't easily find it on the web. You can't find it in a Pytorch hub or Hugging Face hub or somewhere. It was meant to stretch you. It was easy at the same time hard. So I want to know how you guys responded to it. How many of you gave up? How many of you solved it, and so forth. And then from today, we have one final topic to cover. Namely, these are called optimizers and schedulers. It will be the last of the Lego pieces we need to bring together. I'm not going to spend too much time on it, maybe a total of half an hour, 40 minutes, and then I'll go and get started. For the rest of this course, now, the 8 sessions that are there, we are going to do different neural architectures. We are going to do autoencoders, we are going to do variational autoencoders, vector quantized autoencoders, and Wasserstein autoencoders. Then we are going to do corresponding generative adversarial networks. And then, so now from today, almost everything that we are going to do will have generative capability, okay? Or will have the ability to generate data with a verisimilitude, or it will be a simulacra of the data that you give it, right? So in a way, it's a data generator, and by consequence, it is also a fake data, a fake generator, or deep fake generator. Right? Some of these architectures. We'll talk about attention, we'll talk about transformers, we'll talk about normalized flow models, we'll talk about energy models, and we'll talk about Mamba. The pace at which we go completely depends upon the pace at which you folks can keep up in this course. Right? So the more you do the homeworks, the more you review behind the stuff, the better it gets. As I keep saying, the Edinburgh's forgetting curve of 1811 says that in 6 days you'll forget just about everything you heard, unless you go and right now, after the lecture, maybe tomorrow, review it, repeat it, have some repetitions, take a quiz, read the book, go through a few different ways of repeating the same knowledge, and then it's going to sink in. Then you won't forget it easily. Right? So please do that. Now, in this course, we had a homework that I gave, which was relatively, I think the first homework to do with Pytorch. I would like to review that homework. So if you remember, oh, by the way, all of your session recordings are now beginning to show up. If something is missing, I'll keep adding it. This was your homework. So let's go into the homework. When you look at this homework, how many submissions have we got? 3 submissions. It's a little bit disappointing, guys. Try it, submit something. For what it is worth, every time you submit it, I carefully study it. I'll give you feedback on your solutions. Yeah. Right? It's a valuable thing. It's not something you will easily get in online courses. So do take advantage of that. And there is no sense of judgment attached. We are all in a learning environment here. So do please take those. Now, the problems that I gave were 3 classification problems. A model that detects if there is a negative number present. Right? In a set of 10 numbers, in an array of 10. The second one is a model to predict if the sum of the input numbers adds up to greater than 100. Right? Then, once again, output a probability and a label. And the last one is a stretch goal of a model to detect the presence of prime numbers in a set of 10 numbers. I will add, if you guys, for those of you who love the challenge, I'll add one more going forward. And think about it. How would you compute, how would you train a neural network to produce the factorial of a number? You know, remember what factorial is. What is 5 factorial? I think we should ask the youngest member in the team here. Nikita, what's factorial? No? Who remembers factorial?
Yeah.
So what is 5 factorial?
5 times 4 times 3 times 2 times 1, right?
Yes, very good. Yes, that is it. All the numbers from 1 to that number, 1 to n, multiplied with each other. And so, guys, you notice that I'm asking you or giving you homework that are about the foundational aspects of what a neural network is and what it can do. We get so caught up in the fact that the neural network can tell a cat apart from a dog. Or we forget that at core, it is a universal function approximator. So you have to ask this question: does there exist a mathematical function, for example, that can compute the factorial of numbers? And the answer to that is yes. And how can a machine approximate that? And that is fun. So in the same spirit, in the regression, I'd given you these questions: a model to find the sum of inputs, model to find the standard deviation of the inputs, a model to find the maximum. So let me take one simple one. To find the sum of inputs, how many of you did it? Like any one of you who has done this part, speak up, please speak up, yeah.
So, I mean, I created the data set of 10 numbers, and then I created one more data set of y's, and the y's are corresponding sum of rows in the data set, X data set. And I have used the same, there is a file in the, if we have downloaded the initial project, it has a regressor.py, and I slightly modified it and used the same one. And I trained my model and I got like almost 99.9% accuracy.
That's good. And so, so as you realize, a lot of this homework, the solution was already there with you. Right? In the starter code that you got in the neural architectures package, first, do you guys remember that? Yes. If you looked into SVLearn, into the approximator package, you would have seen the regressor there, you would have seen a classifier there, and so forth. So the hard work was two things: preparing the data, creating the training data and test data, and the second part was training it, and then also a training loop, but more about thinking how many layers should there be. So in your case, how many layers were there?
So for classifiers and the first problem in the regressors, I have like 4 layers, in which 2 are like activation layers.
2 are activation layers. And so how many actual neuron layers do you have?
4.
4 neuron layers.
4.
And each layer contains...
Are you talking about the number of activations in each layer?
No, see, how many layers, like how many times did you write linear, right? Remember, 4 times. And how many neurons you had per layer?
Classifiers, there are 5 layers. The last one is sigmoid.
That is okay. That's all right. Yeah. So very good. And per layer, you had what, 128 neurons or something like that?
No, I just put it to 10 because
10
the data set is just
10. A 10, and then second layer?
An activation function,
then
is like a ReLU.
Then?
Yeah, 10.
And then?
And again 10 layer.
10, 10, 10. Yeah. All your layers were 10 size, more or less. Inside, hidden layers were all 10 neurons each. Anybody else would like to answer that question? Who else has done that?
Hey, Asif, so are you still asking about the sum of n problems?
Yeah, so let's look at the sum of the inputs. Yes.
The regressor?
Yeah, let's take the regressor. Let's pin that one down. Regressor, the item number 1, the sum of, how would you find the sum of inputs using a neural network? And you're not allowed to write a torch.sum function on the input.
So in this, again, I don't have a science behind this, Asif, but I had a total of 5 layers, 3 hidden layers.
Mhm.
It went 10 to 24, then 24, 32, 32, 24, 24, 6, and then 6 to 1.
Yes. And
And
what ultimately, how accurate was your summation?
summation was about 98% accurate. Right?
You mean that you most of the time got your mean squared error was very low.
Correct, correct. And
Mean
so when I
squared.
did it as a percentage, it said the error percentage, if I remember, was fairly low. In fact, I'm just, with your permission, I can also run it real quick and just tell you. But yeah, it was the accuracy of this was pretty high.
No, you don't speak of accuracy for regressors. You speak of mean squared error.
Correct.
Of the numbers. So if your MSE was fairly low, that is good. And for classification of whether it's greater than 100 and less than 100, which is related, there you speak of accuracy. So
Okay.
there your accuracy must have been pretty high. How much did you get?
So in
Because
the
that's the same network with a sigmoid at the end, isn't it?
so in the classifier, I had just 3 layers, 1 hidden layer. Right?
Okay.
Because when I was playing with layers, I added 2 layers. In fact, I found the accuracy drop, and I couldn't fully understand why. But in that,
Very insightful. Very, very insightful.
okay,
Accuracy dropped if you added less. Isn't that paradoxical?
yes, and in
And
that,
why?
for the
Go ahead.
first two, the accuracy was very high. It was to the tune of 98, 99%. The prime number, I could only
For the
consistently
classifiers. No,
classify.
name them. Instead of saying first two, name them. The
Yeah,
negative number detector and the,
negative number detector, and then the sum of input numbers in that array being greater than 100.
okay,
Both of them
it
had
was,
accuracy of in excess of 98%.
okay, very
The
good.
prime number, I could only get consistent accuracies in the region of 78%, not higher than that.
Yeah,
There
the
was a
prime
couple of
number
things that I got
detector.
83%, and that was one thing I want to ask you, Asif, is sometimes running the same thing without any changes would change the accuracy. So I'm wondering if there's some deliberate noise also that gets inserted in this whole process, because consistently
Yes.
being able to get only
So we'll
70
talk about that.
prime
We'll
number.
talk about that. So we'll talk in great detail about the prime number one. Yeah. In fact, I deliberately sneak that one in because there is a lot of learning behind the fact that it doesn't do as well as the other ones.
Correct. And the interesting thing over there, I think I posted that on the Slack channel also, is initially when I generated a million arrays of prime number of a million arrays, about 600K of them had at least one prime.
Yeah,
And then the accuracy was about 55%. And
right.
then I just did a Google search to say how many primes are there between 1 and a million. It said there's about 78,000 primes. And I said, okay, what if I try having roughly that order of prime numbers in the arrays, in the million arrays? And so I changed the array number, the test, the array generator to have about 65,000 primes. And the accuracy immediately jumped to, I think, 80% plus. Okay.
Good.
I had no idea why, because I would have thought intuitively that the more primes you have, the more accurate it would be.
No, it's also beginning to
Prime numbers
remember
actually
primes.
affected the accuracy very profoundly.
Yes.
And I don't understand why.
Yeah. No, this is good. And thank you for trying. This field is all about trying something, looking at what happened, and then trying to reason why it happened. And we are going to reason through what you observe. But in this one model, sum and standard deviation, I trust you. And the max, what were your general results?
The sum of
These
10, the
you said
RMSE was 0.75.
very low. Okay. And your number range was?
Number range, this was just a minute, I'll tell you what I think it's, yeah, I'll tell you. I just have to check my that number generator. So give me a second, I'll be able to tell you that.
Yeah, because MSE makes sense when juxtaposed next to the range of numbers.
It's a million. Oh, sorry. Number start range is 0, end range is 1,000. I'm sorry. The sample size is yeah. And by the way, even on the prime one, I found that for the exact same logic, if I change the range of the prime numbers from 0 to 1,000, the accuracy jumped to 90% plus. Then I changed the range of primes from 0 to 10,000. The accuracy came down to, I think, the low 80s or around the low 80s, if I remember right. But then as soon as I expanded it to a million, the accuracy dropped down to 55% again. So there was a strong.
Yes, and Mahesh, you wonder, right? Why? Like, I must be really bent on giving you a tough time to make it a million. It is actually very good thought. I'm just really very happy you tried so many things. Anyone else who tried? Okay, by the way, Mahesh, did you do so forget about the prime number, talk about the regressors. You got all the regressors right, isn't
Yes,
it?
yes.
And what about the maximum in a set of 10 inputs? How often was it right? Like,
Give me a second. I will tell you the mean square. I just need to run it again. But maybe someone else can just quickly, because it'll take a couple of minutes for it to run because I'm using very large arrays. I'm using the million numbers to train it.
it's all right. So this problem actually, in hindsight, I should have put it in the classifier section because it's easier if I just say which of the 10 is the largest. So if you want, those of you who haven't started, they may choose to move it to the classifier section. And the regressors are relatively easy, straightforward. I hope you got it. So you got your standard deviation also in place. What was your network like for standard deviation?
This was, like I said, for the classifier, it was 3 layers, 1 hidden layer. For the regressor,
No, for the standard deviation.
Standard deviation also, yeah, the accuracy was 99. The RMSE was very low. I'll need to just run it real quick to let you know that one.
No. What was your network? What was the topology of your network?
Same thing. So what I did was I have just one classifier for all 3 problems.
Okay, and
so
it
there's
is 4 layers.
One classifier for the regression problems and one classifier for the classifier problems. I use the same.
Same thing.
But different inputs.
Remind me the topology. How many layers? How many nodes per layer?
So I'll tell you, it is a total of 5 layers, 3 hidden layers. First layer is in features are 10, out features are 24. Second one, it's 24 and 32. Then the third one is 32, 24. And then it's 24, 6, 6 and 1. And this I just got with a Google search saying that, this kind of an architecture sometimes yields very accurate results. But again, I don't have an understanding of why this happens.
Right.
And I've run the max, and that I'm getting an RMSE of 18.48. So pretty high.
Very good. Okay. So this one isn't doing that well. What's your number range? From 1 to 1,000, if that's your range, then your standard deviation needs a little bit more work. Okay, guys. Who else would like to volunteer? I know that some of you have submitted, others have also submitted.
I submitted only the first problem.
Okay.
That's it.
Classify. And how well did your classifier do?
I think 90.3%.
For which of the classifier problems?
The first one.
A model to detect if there are negative numbers.
Yeah.
So is there anyone who used only one hidden layer?
Yeah, I used one with 10.
With 10 in them.
10 neurons.
10 neurons. Okay, now I'll ask you this question. Is there anyone who solved any of the problems using just no hidden layers at all, just one neuron? And can it be solved with that? So I want to take
I
that.
tried it for the sum of inputs. I tried it for the sum of inputs, thinking that it's just the sum, so it's just one function, and just it needs to add all the numbers. I didn't know the losses exploded.
Exploded. All right. So a good effort, Kyle. Kyle is your TA, so it's hard to beat her. She's also an all India topper. So, all right, guys. So now, yeah, I'll keep embarrassing you with that news all the time. So guys, what I want to do, and the reason I gave this problem is, I wanted you to think from first principle. See, guys, there is a problem today in our community. The problem is, we have all become fast food junkies. What do I mean by that? Anytime we feel hungry, we rush to McDonald's to pick up whatever it is that's there in McDonald's or Chipotle or whatever it is, and we rush home. Now, as you know, if you do that, soon you'll lose your health altogether, isn't it? So a similar situation has happened with our AI community. The moment there's a problem, the first instinct of people is not to solve the problem, But to ask this question, okay, which fast food place do I go to? Or rather, which hub do I go to? Pytorch hub, Hugging Face, right? Which model should I download? Right? Which one should I fine tune? Are we together? Right? Or your reaction is to start Googling on the internet. So what you lose is what physicists hold very dear or close to their heart. It is that you should think of problems from first principles, the ab initio. So let us think of it from ab initio. I was hoping, so it is the fact that none of you got it. It's a measure of how badly I've failed in educating this. It means I haven't done a good job explaining this. So we'll do this again. I'm going to start asking this question. What is a neuron? A neuron, this is a neuron. It is made up of two parts. Remember, I mentioned that a neuron is made up of two parts. A linear transform and activation of the linear transform, isn't it? So input goes in, let's say x1, x2. Let's say in our case, x10, this is your array of numbers. They go in, and what happens along the way? They form the Z. Z is what? Summation of, what is it? Anyone remembers? So suppose they have weight 1, W2, W3, W4, W10, right? This is Wi, let's say. What is it? W1 x1 plus W2 x2 plus W10 x10 plus bias, plus a bias term. Bias term, right? Bias is just the offset, it's a shift, right? It's a linear transform. And then you activate it. Isn't it, guys? So tell me, guys, if you stare at this problem, can you tell me what's the relationship to this equation?
W's are ones.
Yes. So B is equal to 0, Wi all equal to 1. Right? So more profoundly, you realize that this problem is a linear combination of inputs. It doesn't even need an activation. You realize that. It doesn't need an activation. Just because a library uses activation functions, just because everybody uses an activation function, doesn't mean you have to. A neural network can be a single neuron with just a linear transformation, isn't it? So how would you train it? What would you do? You would just create a linear layer in your Pytorch with input dimension 10, output dimension 1, isn't it? And in your neural net, so this is it, right? You would take the input, your forward method would be what? Input, let's say that input is X, right? It would do, so forward is on the X, right? And actually there's a self and all that. Forget about it. What would you do? You would say, this particular layer, you would apply the layer function, you would pass X through that layer function, and whatever it becomes, you would just return it. Any reason not to do that? What will happen is the neuron, the one neuron neural network, will start with random weight initializations and biases, right? But as you train it, it will figure it out, right? Now, what happens is, and this is something to learn, neural networks are very suspicious of absolute zeros and absolute ones. So they sort of crawl their way towards it, right? And floating point number, it's very hard to have exactly 1 and exactly 0, but you'll get very close to it, Would you? Right. And so if you look at the solution that I posted, we'll walk through the solution in a moment. Guys, does it look obvious now that you did not need to create multi-layer neural networks? In fact, adding layers just makes it harder for the machine to learn. Right? Because it has to somehow simplify the problem repeatedly. Right? Let's look at the, 1 second. So, okay, why don't you ask your question?
Do we even need to train it? Because it's a simple.
No, you train it because the point is that a neural network or a neuron initially initializes with random weights. Right?
Okay.
So you go through a few epochs and then it learns. Right? And what it learns is that there is no bias needed and most of the weights asymptotically converge to 1. You see how simple it was? Right? So that is the benefit of the lost art of ab initio thinking. Likewise, I asked you this question to tell whether the sum is, so you know that you can literally in your mind visualize the answer. You can tell whether the answer, the number, is greater than 100 or not. The sum is greater than 100 or not. How could you have solved it? Suppose I put a bias of minus 100. Right? If the machine could learn that the bias is minus 100 and all these weights come in, x1, you realize that weight 10, z comes in, what will it be? It will be summation of wi xi minus 100 because that's your bias term, isn't it? But this is your z. What do you need to do? When z is 0, your sum is exactly 100. When it is more than 100, z will be positive, and when it is less than 100, it would be negative. Is it making sense? And so what happens when you sigmoid it? So let's say that is the sigmoid function, sigmoid activation function, which I hope you reviewed. How does a sigmoid activation function look? Sigmoid activation function looks like this. Like it's the classic activation function used all over nature and everywhere. 1, 0, right? And it achieves at value 0, this is 0.5, right? So if you pass it through a sigmoid, what will happen? The moment it crosses sigmoid, the probability, the moment z becomes positive, the probability, the sigmoid is producing a probability. What will the probability be? Greater than half. Would you say that was easy? Again, a 1 neuron problem.
So
No?
can you repeat that again?
See, when z is greater, so suppose you train the neural network and it sort of learned and figured out that b is equal to minus 100 and weights are equal to 1, which it will do after a certain number of echoes. When z is greater than 0, sigma z, this is sigma z, will be greater than 0.5. Probability that it is more than 100 will exceed half, right? And so you have a binary classifier that should immediately get it. Are we together, guys? Now, I'll just give you guys 2 minutes to think or 5 minutes to think. Tell me, how should I do? Let's take the other one to tell in a classifier that if a negative number is present at all, right? So here's the thing, guys. Can it be answered with 1 neuron? Think.
Yes.
How?
The weights can be zeros, and for the negative number, it can be the same minus 1.
Now, how would you know? How would the machine learn that? Because the numbers keep shifting. If you give it a weight 0, what if on that 0 landed a negative number after training? So guys, think, how could you do that? Can you do it with 1 neuron, or finally we give up that no more toy examples, let's get real with a full neural network?
So if the range is minus n to n,
Mhm.
In general, the sum, if there's a negative number, then the sum of all these must be close to 0, right? We're assuming that as many negative random numbers we generate as positive random
Yeah,
numbers.
10. When you take a subsample of 10, the average of them or the sum of them is not necessarily going to cancel out because the law of large numbers doesn't kick in. Log of those numbers multiplied. Okay, any more ideas? Okay, guys, see, this is where I would ask you to think. My hope was that I'll teach you in such a way that you get it from first principles, and hopefully by the time we finish this course, you get that. Think again, activation function. Do you know of an activation function that is dead quiet in one range of values and responds only in the other range of values? A ReLU. ReLU. What is a ReLU? So when you think of a ReLU, what is a ReLU like? This is a ReLU, right? Is this making sense, guys? This is a ReLU, isn't it? This purple line is the ReLU. So what does it say? For negative values, it's 0. For positive values, it's positive. So now think about it this way. Suppose I give you some numbers, some positive, there's an array of numbers, A, B, C. Okay, let me just call it X1, X2, X3. This is ugly. Let me rewrite it. X1, X2, X10. Right? So this is your X vector. Is this. What is a minus X vector? All the negatives flip to positive, right? So all the negatives will become positives and all the positives will become negatives. So far, so good, right? You flip them. And now if you pass it through a ReLU, what happens?
Only the positive number will come through.
Yeah, or the original negative will shine through, everything else will die.
Wow.
Right? Do you see how, if you just think from first principles, you can solve it to 100% accuracy, basically. You realize that, right? And so what you do is when you design a neural network, you would do it like this. Your network, the forward step, the forward method, forward of X would do this. It would say that X is equal to ReLU minus X. First of all, you flip it, then you pass it through a linear layer because you need some weights, right? Let all the weights be 1 or whatever it is. It hardly matters, right? Let it learn whatever weight it wants to learn. Linear layer you would need. How many linear layers do you need? 1 neuron, right? This is again your linear of 10, input 10, sorry, input dimension 10. 10. Output is, what would you like to say? Output is equal to 1. And then what do you need? If the signal is positive, even invariant of where the weights are, basically so long as the weights are positive and it learns, it will in a few epochs learn a positive weight, right? It leaves the positive numbers alone, right? It doesn't screw it up. So then what happens? What will the sigmoid do? So again, go back and look at your sigmoid. What does it do to the Z will be positive after that, isn't it? So when I do this is my Z, right? This is effectively my Z. If Z is positive, I can pass it through a sigmoid, right? This is my Z. So the next step would be to pass it through a sigmoid of X again. So the initial X, you flip it, you pass it through this. What happens now?
If it's positive, the output is greater than 0.5 with the probabilities.
Right, and you have solved the problem. Literally. You see how easy it was.
Sorry, I didn't get the ReLU minus X. What did it flip the sign there?
Yeah, see, think of a number. I'll take an array. Minus 7 plus 3 minus 2 plus 11. I'll just take it, so on and so forth. So tell me, when you take the negative of this becomes
7.
positive, right? This becomes -3, this becomes +2, this becomes -11. So what happens is that you get as -x will give you these numbers,
Okay.
right? Now, what happens is when you do ReLU of -x, what does it do? ReLU of -x will give you 7,
7,
0, 2,
2, 0.
0. So all the original positive numbers will yield zeros.
Correct. Correct.
Right? And let us say that they went into a network that somehow figured it out that you don't need to do much. You just put their weight to 1. Right? So what will come out? What will be the z that will come out? It will be a positive number.
Yep.
It is
Right?
0.5.
And what is the sigmoid of a positive number? Sigmoid of a positive number is greater than 0.5 probability. Right? So it doesn't matter how many positive numbers are there. I mean, how many negative numbers are there? 1 or more, or all 10 negative. This would still work.
So, Asif, can you just write this in terms of the linear and then ReLU and sigmoid? Just how would
Yeah,
this?
so I'll walk you through the code. How about that? I'll walk you guys through the code now. Right. So anyway,
That's a quick
I would like
question.
to say,
Asif, I'm sorry, quick question. So in this case, the bias is still 0?
let the machine learn it. It will come to the conclusion that, see, you can set the bias to something and the weights to something else. The machine will decide, but one easy solution is set the bias to 0 and the weights to 1. Right?
Okay.
Or half, or any positive number. So long as the weights are, 1 second, any positive number, you realize that the machine has learned. It will. This problem is actually so easy that a single neuron will learn it so quickly, right? That it may practically be suspicious of itself. It will say, okay.
It says 0, like the bias is 0 here, like because the -3 into.
Say that again.
The 0, 7, 0 into everything.
No, ReLU. When you ReLU, the ReLU of a negative number is 0. So when you pass this vector through a ReLU activation function, what will it do? It will just go wipe out all the negatives. But those negatives are actually positives, right? What you're looking for is you're applying a mask on the array. You're saying negative numbers light up. But ReLU does the opposite. It makes the positive numbers light up. So all you need to do is flip it and then give it to ReLU, and all your original negative numbers will light up. And your problem is solved. Right? So guys, this sort of clarity comes through what? Through hunting through Hugging Face for a model? No, it comes obviously by thinking from first principles. And sorry if it looks like condescending or talking down to you, I really apologize. But for me, it's a little bit particular because I've managed a lot of large teams. And quite often I've sat back and smiled when people bring solutions that scare me with the amount of hard work and sophistication they have put in. When sometimes you have to say that, let's think like a scientist. We are all called computer scientists. Computer parts we all do, but where has the scientist part disappeared? Right? Sometimes we need to be a little bit more particular about that. So with that, let me show you the solution. Right? On this Windows machine, the solution doesn't quite.
Asif? I have a
Yes.
comment. For me, my linear algebra is not really good, and I'm refreshing. And so as you're teaching, I'm starting to understand the principle, the concepts, but the execution I struggle with because when there's a lot of math, I have to read it slower because I'm not as knowledgeable. But as I read the other books, and it covers a similar material, but in a different fashion, either code first, then math, per se. Because I understand the principles, I can understand what I'm reading faster and I can catch up, but I'm lagging by like a lecture. Because I get the principles and then I start to read and really go into it and I start to understand. And I don't know if anyone else is experiencing that, but that's my experience on my end is I'm getting the principle, but then I got to go over it multiple times for it to start to cement in my mind.
Right. No, this is awesome, Sarah, because in some ways, like we computer scientists have forgotten principles first thinking. They have gotten very hacking first thinking. Right? We have people who the moment we see a problem, the first instinct is to pull up our keyboard and say, what code do I write? And so it's good that we, a little bit. So anyway, the whole purpose of this little homework was that, so guys, would you like to solve the rest of them on your own, or should I go on giving all the solutions?
I think we'd like to try it on our own.
Yeah.
But given
what I was going to say was, again, solution to your point, right? The first principle thinking. I don't know how many of the people here, say confidently that, hey, I could have thought that ReLU, if I apply ReLU, it would have given me this. I 100% wouldn't have even, thought that way. So at least from the thought process perspective, maybe if others are not interested, I can connect with you independently to see what the thought process should be for solving the other problems. But if you would want to, go into that mode, I would love it. But if majority feels that they are going to try it by themselves, maybe I can do it offline with the TAs or you.
Yeah, you could reach out to the TAs. You can reach out to me. So you're showing up as SR. May I please know your full name?
I don't know why it's showing as SR. This is Anand.
Oh, Anand. Okay. So yes, Anand, you do. Your point is valid. You can ask me. You can always come here. Ask
But Asif, can you explain? I'm totally out of programming. For this one, right? Which problem did we solve? What is the correction that you're doing for the solution that others shared, right? I'm still trying to grasp this.
Okay. Let me recap what the problem was. We are trying to do first this problem, a model to find the sum of inputs, sum of 10 numbers. Right? So when you look at that problem, everyone did what I suppose these days is second nature. As programmers, we all said, all right, let's whip up a neural network. And very helpfully, I'd given some neural networks in the previous installment of the code. So almost the only question people asked is, okay, we need to prepare data, and then we need to run it through, just modify the network to our choices, and then run it through it. Right? So, which is right. See, all of you got good accuracy or good results, good performance. All of you got. So is the solution practically right from a real world perspective? Can it drive a product? Absolutely. And perhaps as an engineer, that's all that matters. Right? But if you're in the pursuit of elegance and simplicity, then you can go back to first principles and ask, what is, let me think. And this is one of the things I would suggest, that see guys, every day a paper comes out. And most of these papers that come out, the good ones, they have one simple idea in them. Right? But that simple idea is often expressed in 30 pages. Right? Because it's the formalism of research. You have to explain the method, you have to justify it, you have to prove that it's correct. There's a proving part of it. Then you have to give experimental results and many, many things. But you glean one idea. You will have a far better time reading research papers, almost immediately grasp what they're trying to say, if you are in the habit of taking things apart and reasoning through a problem from first principles. And so the sort of learning that I wanted to bring to you guys today is that sometimes when you think from first principles, a problem is far easier than you think. Far easier. Now, don't you guys feel that in hindsight, it looks dead obvious? How many of you feel now? Right? Many hands, almost all hands are up. Right? It feels dead obvious. Right? So the thing, again, and I'm trying to create a mental shift or a cultural shift. Why didn't we think of it? Right? Because partly me, I conditioned you that neural networks have many layers. Right? And I deliberately gave this problem first to take you in that direction and then to snap you out of it. To tell you that there is value in ab initio thinking. Go ahead, Albert.
So once you do the review and then you get 7, 0, 2, 0 on, you take a sigmoid of it, so 7 becomes close.
No, not sigmoid. What does Z do? Remember, that's still a vector. You need to convert it into a number. So it needs to go into the linear transform part of it. This then goes into W1, 7 plus 0 W2 plus 2 W3. You see that, right? And so long as these W's are positive, what will happen? The Z will be positive. And if Z is positive, sigmoid of Z will of course be greater than half. So there's a greater than half probability that you're looking at negative numbers in the array. That's it.
So sigmoid goes from 0 to 1.
Sigmoid goes from 0 to 1.
So any positive number would be at least 0.5.
0.5 or more, right? That's the nature. So guys, lessons here. Activation functions are not things you take mechanically. In our course, we have a whole section on activation functions. May I give you guys another homework then? You realize that it's important to know them, make best friends with them, right? So may I suggest a homework, which is that read this activation function. Do you notice last time we covered activation functions? I said there are quite a few activation functions. Here are my notes on the most important activation functions. I don't know how many of you read it. Please do go read these activation functions. Okay. Here I've created a very short list of the most important activation functions: sigmoid, tanh, ReLU, leaky ReLU, right? And so on and so forth. And it gets a little bit more sophisticated as you go along.
You didn't cover activation functions, only back propagation, and you said we'll take one more session to cover.
Oh, I didn't cover activations.
But we did,
We did activation functions.
before this.
We did, yeah. But I covered it briefly. I just said that remember I said deformation functions. That's what makes it a universal approximator. So maybe I'll cover it more. See guys, here's the thing. We have a limited bandwidth of, 8 more sessions. So I have to rush a bit. So some part, you have to put in the energy. So if you look at the activation functions available in Pytorch, it's a pretty rich list here. This is what Pytorch supports. Now, see guys, you may not be able to understand or remember all these activation functions, but from the document that I wrote, even if you remember the top 4, sigmoid, tanh, ReLU, leaky ReLU, you're well on your way, right? And others then are more useful. For example, in the latest transformers, right? For example, BERT, etc. What do they use? They actually use a more sophisticated activation function, and through trial and error, they discover it. They use a GILU, right? That is a Gaussian superimposed upon a ReLU, right? So that is it. If you really want to go deep into activation functions, here is the notebook. 3 decades of activations. So, there are people who have taken it seriously enough to create 400 separate activation functions, right? Each having its use. And this is the research paper from that. And if you look at this research paper, it is a substantial research paper. It goes down to 400 activation functions described in detail in no less than how many pages? 107 pages, right? So now you're not going to read 107 pages, quite likely, unless you need to. Sometimes you need to refer to them and see which one is best for your needs. But at least know the short list that I gave you guys, activation function. Here is a Jupyter notebook of these activation functions. But I will cover these activation functions in a moment again, just as a brief. So this is a Jupyter notebook of those activation functions, sigmoid, tanh, etc. And the shape of it. You see the shape of it. Okay.
Yes, one question. Is there all these functions are invented for neural network or DSPs, digital signal processing?
No, these are all neural network activation functions. Of course, they were not all invented here. Some are borrowed from the different fields. Sigmoid has existed for the longest time, the logistic function and so forth. So that is that. So I'll give a very quick recap of what the activation functions are. The activation function basically, see guys, in a neuron, right, for it to be a universal approximator, you need a linear transform which is z is equal to bias plus w dot x, right? Dot product between the weights and the weights and the input vector. This part we know, isn't it? Is the linear part. But see, mathematically, there's a result that if you do more linear transforms on linear transforms, you're only going to end up with one giant linear transform, right? So I'll illustrate that. Examples of linear transforms are stretching or unstretching, squishing, but I'll just call it stretching, scaling. So if you scale something and then you scale it again, it is the same as having scaled it once with the sum total result of these two scalings. So suppose you scale first by factor of 2 and then a factor of 3, it is the same as scaling it by a factor of 6. Does that make sense, guys? Right? It is still a scaling. Scaling is a linear transform. Similarly, if I rotate a vector and then I rotate some more, right? Ultimately, it is still at some rotation from the original. Does that make sense, guys? Like, for example, if I take a vector like this and I rotate it to this, first rotation, theta 1, and another rotation, theta 2, you can come up with a grand theta total, which is basically theta 1 plus theta 2, isn't it? Now, I won't go into the linear algebra of it. Usually these are elementary exercises given when you take a course in linear algebra in school, right? They'll give you the rotation matrix and ask you to prove that applying two rotations, one after the other, leads to just a grand total rotation. Anybody remembers those? Maybe remembers it with horror, those trigonometric. Right? So anyway, so the bottom line is superimposing linear transforms on linear transforms will only create an overall linear transformation of the input. Right? So when you try, so imagine that you have a line, right? Y is equal to X. But what you want to do is you want to convert this. What you really want to approximate is this line. I'll just take an example. This line, right? You realize that I need to bend the line. I need to deform the line. Does that make sense, guys? I need to deform it. Therefore, what you need is after the z needs to go through a deformation function. I call it deformation function because to me it's more intuitive. More technically, it is called the activation function or nonlinear function. So what should a good activation function look like? What should be its properties? Well, what's that?
I mean, adding up
deformation, yeah. It should deform the input somehow, right? So let us think through it. What should a good activation function look like? What should a good activation function look like? So guys, always keep this in mind that you have something like a line. This is your starting point. This is your z, right? Y is equal to X, a straight line, and you're trying to deform it. So would you agree that first quality is it has to be non-linear? Does that make sense, guys? The other property that it should have is that it should be continuous. Right? Because what happens if it is not continuous? So for example, if I have a function that looks like this, and the values are undefined in between. Right? First of all, values must exist everywhere, and it should not jump. Like for example, it should not even have discontinuities. If it has discontinuity, what will be the problem?
The neuron will not,
unstable reactions, right? Very small changes of input will lead to significantly different activations. You don't want that because at the end of it, and this is something that I should say, you always approximate it with more or less a smooth function. You hope to create a smooth or a continuous function out of it. So it should be continuous. Then then there are two properties which people thought historically are important. Historically, there are two more properties that people thought important, that it be differentiable which geometrically, if a function is differentiable, geometrically, what does that mean? Anyone? It is smooth, right? Smooth curves. So it turns out mathematicians are very much in favor of smooth rather than jagged or sawtooth curve or surface. Differentiable, just in practical terms, geometrically, means there are no bumpy edges, right? Nothing to poke at you. This we thought historically that it's an important quality of a activation function. The other thing that we thought was interesting was monotonicity. Now, monotone or monotonicity, what does that mean?
Continuously increasing.
Continuously, like its movement. As you keep on increasing x, the x-axis, it is either increasing or saturating or decreasing, but it doesn't change its mind, right? Are we together? It doesn't change its mind. So, for example, this is monotonically increasing. This is also monotonically increasing. This is monotonically decreasing. This is monotonically decreasing. But this thing is not a great function to go for, right? It's going to, people thought it will drive the neural network crazy. The other thing people thought that was good was asymptotes. A fancy word for saying saturation points. So let us historically think of something that is nonlinear, continuous, smooth, increasing, and saturates both in the positive and negative x-axis, right? Would you agree that if this is the x-axis, whether it is here or here, it needs a saturation point? Let me do this. It needs, at infinity, at very high and low values of x, it should saturate to some value, isn't it? Then what should happen? It should gradually start increasing, but if it starts increasing, it surely shouldn't decrease after that. It has no choice. And if you use the word differentiable, it means it has to happen gradually. And so it will look like this. Are we together? Does it make sense, guys, that it will look like this?
Yeah.
Right? So this class of functions, they come from, so imagine that you have an S. This is your S in English, right? And imagine that one person pulls the S in this direction, another person pulls the S in the other direction. Then will it begin to look like this? Right? It's a stretched out S. Right? When you have, yes.
Why are the other four factors important
These other four factors, it turns out, for simple reason, it makes, we found that nature practices this sort of activation. For example, our nerves follow this sort of activation. Right? So what happens is, for example, if you look at the signal transduction between two neurons in the brain, what happens is that there are neurotransmitters in between. So when the signal has to come, those neurotransmitters start binding. And so there is a good bridge for signal to go across. But there's only so many neurotransmitter molecules there. So it saturates. There's only so much activation you can do for that. And so all over nature and everywhere, people found that asymptotes or the saturation points were a good thing. And because people initially were trying to get inspired by the human brain, for doing this field, they thought, yes, we must have this. Right? So that's a very good question, actually, that Healthy bring in a perspective here. So now what happens is this kind of things, because they start, it is very fittingly, they are all called sigmoid functions. They are a whole class of functions. Notice the S that I've underlined. There are many sigmoid functions. Any function that looks like this is a sigmoid function. The classic sigmoid functions are the logistic function, which is 1 plus e to the minus z, right? This is a sigmoid function. It is, right? The other is the tan h. The other is the error function. What is error function? Error function is the integration of the bell curve, and so on and so forth. There are many, many activation functions available that fall into this category that they are sigmoids. Now, within the neural network community, though, there is a little bit of an abuse of terminology. Most of the time when they say sigmoid, they are specifically referring to this one, logistic function. Are we together, guys? So you will see this abuse of terminology. And sometimes when you come across different cultures, or research paper written by mathematicians versus neural network people, or other areas of machine learning versus that, there'll always be this thing. Oh no, it's a logistic function, or things like that. So sigmoid, strictly speaking, is a class of such activation functions. Now, one of the realizations that Geoffrey Hinton had was that saturation points are actually not good, right? Because what it does is, once your input becomes large as the signal propagates, it basically saturates. And so look at this. What is the gradient of the function here? 0. And what's the gradient of the function here? 0. So he made the pretty bold departure from what was well-established understanding. And he says, what if we throw the saturation points, or the asymptotes, out of the window? Right? So then what you do is, he just said, okay, let it be like this, the simplest, let it keep growing linearly. Y is equal to x. Right? And while we are at it, how do we bring non-linearity? That you can't throw out of the window. Right? So he says, okay, this is it. Right? It's 0 in negative direction. And it turns out that this is exactly what a diode is. If you think of a diode, those of you, I don't know, it's a device in electronics in which current can go in only one direction. In the other direction, you just can't go. Right? Or it's like one-way traffic. Right? One-way highway, you're only allowed to go in one direction. Right? So this was the discovery of the ReLU. And what he found is, when you do ReLU, you don't have the problem of vanishing gradients. You do have. What's the gradient here? 0. Right? So then people thought, oh well, ReLU now needs a version 2. Right? So they came up with, as you might have guessed, a tiny little in the negative direction also there is a line. Right? So there is a tiny non-zero gradient in the negative also. So that you never have vanishing gradients. So this was called the leaky ReLU. ReLU stands for rectified linear unit. Why? Because it's literally line in the positive direction. It's just a line. Y is equal to x. And rectified means this comes from electrical engineering, a diode. Current goes in only one direction. Make sense, guys? Right. So then people came out with leaky ReLU. Right. And then some people said, we are not quite happy. We don't like giving up the sigmoid or giving up the error function and those things. So what if we could sandwich both of them together? Right? And so all sorts of hybrids began to pop up. Like, for example, you could have an activation function which broke monotonicity. So it turns out that if you have an activation function like this, okay, let me make it bold. Activation function that goes like this, right? mostly linear in high positive regions, mostly zero in very low positive regions, very negative regions. Gradient is never zero, but there is a lot of activity around zero. Why would you prefer an activation function that looks like this? The reason for that is we know empirically that the weights, they are all perturbations around the weights, they are all of a normal distribution. If you take a sufficiently large neural network and you just plot the weights, the values of all the weights, which is very easy, right? You will notice that they seem to have a bell curve distribution. Most of the values are around zero. It's a good idea. Let's have a lot of activity around zero. So there are many variations that have come up, but the one thing that you should know and is that ReLU is this. It's the most commonly used activation function, especially when you're learning, right? In practice, in transformers, you go to GILU, but GILU is a little bit harder. It's basically this green thing that that's GILU. So then you break this. So what happens is that you start breaking some of these assumptions. Monotonicity, do you notice that got broken? And ReLU, right away, the first objection to ReLU was, what happens around zero? It loses differentiability, right? But people actually found that in practice, it doesn't matter. Because anyway, computers don't have a notion of absolute zero. Right? Floating point numbers, you never really get absolute zero. So you don't worry about it in practice. So that's a little bit about activation function. And so what do activation functions bring about? Deformations. Once you have deformation, that property is the property that makes neural networks into universal approximators, right? So it is a conspiracy of many neurons, each bringing in their own little deformation that superimposed together leads to the ability to approximate just about any function, right? Or deform itself to any geometric shape. Are we together? Right? So what I'll do is I will just quickly show, I guess I should show this in code. I'll just show it in GitHub quickly, because on this machine, I very much doubt that this would work on neural network. So let me, neural architectures. So this is something I've given you guys. What I've given you on your portal here, let's go here, Pytorch. The partial solution that I've given you is just put it in your SVLearn folder. It's code. It's a new module you'll add to the SVLearn folder. What is that? In other words, you notice that there is a new module called arithmetic. I just zipped this, which is in the SVLearn folder of your previous project. That is it. Nothing else. Huh? Now let's go and look into this thing, because this homework was all about arithmetic. So let's look at the easy ones first. Init, nothing special here. It just is a convenience thing. It's a Python thing to just give you convenience that you don't have to remember actual file names. Then we'll go to the data generator, because this was a reasonable part of what we were trying to do, isn't it? Okay, let's look at this. So far, so good, guys. Arithmetic, you initialize it. You say how many, by default, it will produce 1,000 data points, unless you ask it to produce more. It will produce a 10-dimensional array, right? Convenient for our homework. And it will take a limit of 1,000. What it means is that if you ask it to produce numbers, so for example, let us do that. The first method that's important is the generate inputs. Let's look at this. Generate input. Generate input. So this is something called a random number generator. Python has many utilities to generate random numbers. We are using one of them. And what we are saying is, generate numbers between, in what range? Minus limit and plus limit. So if the limit is 1000, it will go from minus 1000 to plus 1000. And how many things to generate? How many rows and how many columns? Rows would be the number of instances that you want of data, and columns is the input dimension. This line makes sense, guys? And then it turns out that if you use NumPy, so this is a little bit of a bridge you have to cross. If you do it with NumPy, and by the way, I deliberately took this homework and tied it to scikit-learn because I assumed a lot of you are familiar with scikit-learn, right? So made it a little bit friendlier for that. But going forward, we'll introduce ourselves to other frameworks. So there is a bridge between scikit-learn and Pytorch. It's called Scotch instead of Torch, Scotch. Yeah, SK from scikit and Torch, Pytorch, Scotch. So we'll see it used. So you have to convert it to float 32 because GPU, no one does 64-bit computations. Way too expensive. Right? Now, and you don't need that because your weights and biases are never large. You generate, so first of them is generate, let's take the simple one, generate summation data. How can I generate it? I go and generate the data, and what is the y? Y should simply be the sum. Does that make sense, guys? Should be the sum of those rows. Each row, when you do axis is equal to 1, you're summing along the horizontal direction, the rows. So that becomes your y, and it will return the y. Generate max data. Also, hopefully looks easy. Right? It's repetitive after. Standard deviation, also easy, because these are all functions in NumPy. Negative data, how do I generate negative data? So what I did is,
it's not the random generator generates a negative number.
Yeah, so what happens is a random number generator, the input generator, will generate 10 numbers, some of which will be negative. So what I do is, in a little bit, you have to do, I first create a data set, first half of which is just positive. How do I do that? I get the array of all the numbers, some of which will be negative, and I just flip their signs to positive, right? So what will happen is I'll get half the data that is positive, and then, so that's what I'm doing. I'm going through only half the rows. Do you see me? Go through only half the rows. And so half the rows I do it. So top half is only positive. Second half may or may not be positive, right? And invariably it will have some negative number. And then what will happen is you shuffle it, right? Shuffling is important. Otherwise, it will be hard for your machine to learn.
I observed. I did shuffle them.
Yeah, if you don't shuffle, you get into trouble. Albert.
What's the purpose of making the first half negative?
No, I needed positive and negative test cases for classifier. I wanted some cases in which there were no negative numbers and some cases in which there were negative numbers. Remember, the problem was detect if there is a negative number in the input. So I gave, let's say, 50,000 cases in which there were negative numbers and another 50,000 cases in which there were no negative numbers.
So why couldn't you just generate some negative numbers and positive and concatenate them together and just give it?
You could have done that. You could have done it in many ways. This was one easy way I did it. Right? So you can do a little bit of a printout and so on and so forth. So that is this easy to understand, guys, so far?
Mr. Why you just flipping just the first half of the data?
See, I need some rows which are positive test cases, which have negative numbers. But I also want some rows in which there are no negative numbers.
We cannot know the random generator generation, right? So this is forcefully generated.
Yeah. See, random generator, if it generates 10 numbers between 1,000 and minus 1,000 and 1,000, very high likelihood that there will be at least one negative number. Right? So how do you create an array? You need some test data, training data, which are made up of only positive numbers, isn't it? You do need that, right? Otherwise, how would you train the classifier?
I saw, I thought like in that array only half you were changing.
No, no,
Just
no.
in the
rows, in the rows, in the rows.
the
Half the
entire
rows.
set that was done, only half of it you.
Half the set,
I
you
see.
have half the set is positive test
Positive,
cases, half
okay.
the set is negative test cases. Right? And that is what I do. At the end of it, you notice that I I return it like this. Right? And so now let's look at the calculators. Right?
So shuffle, you have to shuffle only in dimension 1, right?
Yeah, shuffle the rows, don't shuffle the columns.
Yeah, but is that
That's what
custom
it
function?
is.
Okay.
Yeah, shuffle assumes rows unless you ask it to shuffle the columns. So it will be happy to do that, but not terribly useful. Right? So now let's look at another function called fit. So this is the function where nothing special. What I did is that the boilerplate code, which is that you take a regression model, you give it the training data, you you train it. Those of you who are used to scikit-learn would love this, right? You remember that last time I showed you a different variant. I showed you the pure Pytorch variant, right? In which you went through epochs and batches. So I wanted to show you a different way of doing it, which is also there. The old way. So because of the scikit bridge, you can just do it in one line. You can make the predictions, and you can see the advantage of this is the scikit has a lot of tooling for model metrics, confusion metrics, and all of those things. And there are beautiful visualizations that Yellowbrick library has created. Yellowbrick SK library has created beautiful visualizations. You get the benefit of all that. Right? So this is that. It will just go plot it out. And likewise for the classifier, the code is almost the same, except that here you don't care about the mean squared loss, you care about the confusion matrix. Now comes the actual calculator. What does it do? Right? Oh, by the way, if you guys are using Greek symbol in your code, in this one I eschewed, I didn't use it. Remember that Python assumes that your code is written in ASCII. It is a good practice to put this line or something like this that will hint to the machine that Unicodes are present. Right? So let's look at this line by line. Import torch. What is torch? Pytorch. And from torch, you import the neural network module. NumPy, we're all familiar with. Scotch. Scotch is the bridge between our old familiar scikit and Pytorch. Yeah. The torch function ReLU. Does that look familiar, guys? Of course, we know ReLU, right? And optimization, remember, this is the one that does the gradient descent for us. So here, I would like to give you a practical suggestion. And if you have to just pick a default, always pick Adam W. Right? It's a pretty good default choice to pick. Right? It is very well behaved, right? And one of the state-of-the-art ones. This import rich print is just a pretty output on the console. Let's look at the network. I create the network. Oh goodness, what do I have? One neuron, right? Because if I give it 10 and the output is just 1, look at it, 10 to 1 by default, right? So I have just one neuron with 10 inputs going in, 1 output. You can count the neurons by looking at the number of outputs, right? 1. What is the forward looking like? And I like to read through this. The forward path is a feed. So you always need a forward method, isn't it? In a Pytorch neural network, if you have been reading the tutorial, which I hope you have been. So, and this is a point we are making. If you think about it, we do not need any activation function here at all when you're doing the sum. The output is simply the sum of the inputs. The activation function is the identity function. By the way, identity function, Pytorch very helpfully provides that in case you want to apply that also. Right? So we can use ReLU. Try it out. You can use ReLU, but you agree that it's unnecessary. Right? No hidden layers necessary. Guess why? I explained to you why. Parameters are the regression inputs. Output is the output prediction. Does the code look obvious now, guys? Does it resonate with the picture we drew? Right? So one neuron solves it. By the way, how well does it work? Because I'm not sitting on my Linux machine and I can't run it, but I'll do, just for a moment, I'll unshare mine because I have to open my email. I'll show you.
Can't you tunnel into your machine?
I can, but lazy. Right? This machine I don't like use for that sort of activity. Okay, there we go. And let me show you. All right, guys. So I'll show you how this single neuron works for your summation. Right? After 40 epochs, after 30 epochs, 32 epochs, what is your, so the first columns are epoch number, training loss, mean squared error loss, validation loss. You split some data for validation, right? And, oh boy, what is the loss at the end of the day? 0. The neuron immediately fixes it out. Now, I bet you if you use a more complicated network, you probably didn't get to 0 loss. Did anyone get to 0? Maybe, maybe not. I don't know. I'm curious to know, with a more complicated network, when you guys did sum, what was the residual MSE that you ended up with?
Very little, but not 0.
Very little, but not 0, yeah. Right? But here, see, it has. And in fact, what's the correlation between reality and, this is the correlation matrix. What's the correlation between reality and prediction? 1. Exactly 1. Then, for the classification, which classification? So I have deliberately given you 1 or 2 answers, guys, so that you don't just say, okay, now that I have the answer, there's nothing to do. You try some out. So there, let me see which one did I do. Which
yeah, so one question.
Yeah.
So you removed the. So why is it that if I see the I can't see the light?
Okay, let me turn off the light.
Yeah. Around 29 to 30th and 32, that is when it suddenly drops up, right?
Yeah.
So why is what might be happening at 30th? I mean, why is it?
No, but remember, epoch is made up of thousands of steps in between. Right. So very rapidly, one of the weights that was hanging around somewhere else begins to slide in the right direction.
Okay.
That's what it is.
I see.
And so one of the things I will give you as an enhancement is actually print the weights and bias of this neuron and see, does it agree with your intuition? Can you please do that? Right. Do that. All right. The next thing that we'll take is
to beat it up that many times to kind of get till about 40 epochs, right?
Yeah.
Because we knew it would go till 40. Yes. And we knew the right answer, right?
No, it's through experimentation.
Yes.
And playing with the learning rate and so forth. And so you know that it's going to converge.
Yes.
You just have to ask when it converges.
Right.
Yeah. So, yes.
Instead of NumPy, can you use tensors?
Yeah. So Albert asked this question, why did I create my data using NumPy? Mostly to give you guys a soft landing. We are coming from, let's say, previous experience in data science using scikit-learn, which is NumPy based. So I wanted to give you a soft landing. But everywhere you see NumPy, literally drop-in replacement of Torch. Because Torch API completely mimics the NumPy API. Are we together?
Have all the functions?
All the functions of NumPy are, not all the functions. All the important functions for neural networks that are there in NumPy are all there in Torch. So maybe you can take this as an exercise. Just do a drop-in replacement. Wherever you see me use NumPy, just replace it with Torch. So if I do numpy.random, do torch.random. If I do numpy.whatever, replace it with numpy.max, do torch.max. It will always work.
Fast on GPU.
And it will run faster on GPU. And so, guys, that is the other problem that I gave you is negative number, detecting the negative number. So, guys, look at it. What do I need again? By the way, here, I left you guys with
minus.
Yeah. This particular example, I left you with 2 of these. Right? But do you really need 2? You don't. Right? I was explaining to somebody what happens when you have more layers and something to convince that it converge faster or not. So I did that. Actually, I should update it. You just take this layer out. It's not necessary. And take this part out also. That's all. All you need is this line. But I'll put the updated code. In a little bit, I'll push the updated code. Actually, what I have given to you guys is the good code. If you download from the course portal, you will see that I've used only 1 layer, 1 neuron. Right? The solution actually has it. I just haven't pushed it to GitHub. Right? because people come to me, ask questions, and then we start mucking around with the code.
As if terminology wise, if it's one neuron, is it considered one layer or 0 layer?
It's a one layer neural network,
One layer.
but 0 hidden layer network. Right. That's it. So, I mean, at that moment, it doesn't matter. If you just say, I have a, or if you want to be really technical, say, I have a perceptron. Perceptron network. Right? So, guys, with that, I will end the discussion of today. And look at the loss that, the loss that came from this was, look at this. As you expect, right? Because there's a deformation function sigmoid, it will never achieve complete perfection. But out of 100,000 rows, it got 3 wrong, detecting negatives. Right? And the reason for that is there is no more gradients left to gradient descent on after some time. You notice that it is just all, the losses are all stable. They're not decreasing anymore, isn't it? So this is a problem of vanishing gradients. It comes very close to the right answer and then just sits there. So we will end this session with this homework explaining session with this. Did you guys find that useful, this homework? So think about it, guys, and let me know if you, like, ideally, I would like you to think about the rest of the problems.
How do we submit the?
Oh, there's a submit button.
No, I mean, I know there is a submit button, but how do you evaluate the forms? Like,
I will just put some comment. Yeah. You submit your code and we'll read it and we'll just give you some feedback. Submit your output also. Like what was your net loss function like I have given here. Submit that, submit your output, submit your code, and then we'll give you some feedback on this. All right. Are we good? Are we good here, guys? Any other questions?
One dumb question. I understand the classification, but what's the regressor? What does it do? I mean, what does it do?
Regressor predicts a number. For example, sum.
Okay.
Sum of inputs is a number. Anytime you predict a number, it's a regressor. That's it.
Is it classifier? Just backward up. I can say if you get a number 1 from the thing like the that's classifying what it is. That's what you mean.
Yeah. See, classifier is the ability to distinguish something from something else. So a cow from a duck, a positive number from a negative number. Right? So when you say, is the total greater than 0? Answer is yes and no. Right? It could be either yes or no. So it's a choice. Whenever you're given a choice and asked to pick one, that's classification. Yeah, both of these are supervised learning. Whenever you give training data, label data, to train the machine, it's supervised learning.
There is no label. We are just saying like 2 or 5.
No, that's the label. That is the label.
That is the label.
That is the label.
Is it always A versus B, or can it be A versus B versus C in a classification?
No, it could be anything. So, for example, if I give you a picture and I ask you, which animal in the zoo is it? Okay. Well, you might have something like 100 or 200 animals. And now you have to pick an answer from those. So, whenever you have to pick an answer from a finite set, you call it a category, and each element is called a class. For example, cats, dogs, these are called classes because, 2 dogs may be different, but they're both dogs. Right? So you say that whenever you're predicting into a categorical set, then it is a classifier. There is actually, for those of you who are interested in philosophy, there is an old philosopher in India who, to the best of our knowledge, made a statement close to 7,000 years ago. He was the founder of a particular stream of philosophy called the Sankhya philosophy. Right? And I'll let you dig up his name. Let it be fun for you. Come again?
Is it Kosambi?
No, Kosambi was much more recent. He once made a statement which people have thought about a lot. And obviously, everything in philosophy is debated. Nothing is ever considered right. That the knowledge, much of what we call knowledge, is the brain's ability to classify things into classes. So we are a prediction machine. See, if you encounter a cow and you have never seen a cow, you wouldn't know what to make out of it. But then you try to decompose it and you say, well, it has legs. I've seen horses with legs or something like that. But if you came across something entirely bizarre, you would not be able to make head and tail out of it. That's ignorance. But the moment you see a cow and you say it's a cow, you have essentially grasped the essence of all cows. And that is knowledge. And he said knowledge is the ability to generalize from instances to the classes within a category. Right? And obviously, from a machine learning perspective, this is certainly true. Right? This is how machines learn. With that, I'll end our session. Let's take it. Go ahead.
Question, sir. What is wisdom, sir?
Oh, no, I don't know. Science doesn't deal with wisdom. You can't quantify it. If you can't quantify it, it is out of bounds.
So, on the output, we have confusion matrix.
Yes. What is a confusion matrix? Okay. Confusion matrix is, suppose, okay, so this question has come from the audience. What is a confusion matrix? And let me explain that. So guys, at some point, the visual or any one of these books, get onto it, but let me give you a brief one. Let me scroll down actually a little bit. See, suppose the reality is cats, dogs, right? An animal can be either a cat or a dog. Now what happens is the machine predicts cats, how often the prediction. So let's look at the y hats. Prediction. This is the y. Right? And you can write it, you can interchange transpose the rows and columns also. Cat, dog. Yeah. These are your predictions. So what happens? This part would be how often a cat is recognized correctly as cat. Isn't it? These are your true positives. Right? What about this? Suppose cat is the positive instance. Right? And this is true negative. It's not a cat. Right? True negative. Now, what about this? A cat has been misrecognized as a dog. So it is a false, false positive, false negative. It's a false negative. It is not a dog, it's a cat. And this is a, what is this?
False positive.
False positive. Right? So this axis, the false axis is the bad one. Like this is the bad problem. So the more elements you have here, it is not good, right? And the more elements you have in a confusion matrix here and here, the better it is. And out of these are evaluation measures. So please take this as a homework. In classification, the metrics people talk about are, the most common metric that people talk about is accuracy. Let's talk about that. Accuracy. Accuracy is this green over total. So that here would be true positive plus true negative over total. Like how often you got it right, right? Then you have precision. We call F1, F score, F1 score. Then you have something called area, ROC curve, area under ROC curve, these are all metric, and there are many more, there are half a dozen more. These are all ways of telling how good your model was at making predictions. So I want
One
at
more,
some
sir,
point,
positive predictive value, PPV.
yes, yeah, PPV, and so on and so forth. There are many such things. So I would suggest that if this is your first machine learning class, the yellow book of the textbooks that I recommended, the yellow one, remember the visual deep learning, has in the very beginning, yes, this one, has in the very beginning an excellent chapter that talks about the model metrics. So please do review from that, or review from anywhere, Wikipedia, etc. These are basic things. None of these ideas are deep. They're just common sense ideas. But you need to know that. You need to know.
So that's the added homework assignment?
Yeah, let's add
metrics.
Yeah,
Okay.
the model, both for regression and classification.
Okay.
Right. So I'll pose you this question for the break, and we'll take it up after the break. Why people often boast about the accuracy of their model? Why is it misleading? Why can it be misleading?
Sometimes these are subjective, right? False positive, false negative.
No. They're not. Machines don't.
Repeat the question.
Under what circumstances? Like, why should you not blindly trust accuracy?
Because you don't know their false negative and false positive numbers.
No. Think about it, guys, in the break. Let's take a 20-minute break. Today, we'll have a bit of a long session, guys. See, we have a choice. Either we can just continue discussing some of these things and defer the topics to next week, because I was going to cover optimizer and I was going to cover autoencoders and neural architectures. We can push it to next week, but if you guys feel we should cover the model metrics, I would be happy to do that a little bit, because it's 9 o'clock now and we have half an hour left. So if we take 15 minutes, it will be 9:30, right? Would you prefer that we continue discussing homeworks and model metrics and other things around it after the break?
I recommend 5-minute break, Asif.
Okay. All right, guys. So let's take a 15 minutes break and then come up with a decision. What do we do? All right.